Good afternoon. So I'm going to be talking about, broadly speaking, agriculture and the impacts that agriculture have, or the effects that agriculture has on our water resources. And the particular lens or angle that I'm going to take is one in which food is a necessity, and the other products of agriculture, fiber, fuel. And in order to achieve the objectives that we have of sustaining our current well-being and finding new markets and adapting to changing environments and changing consumer demand, we need to better understand how agriculture impacts water resources, water quality, and how that also feeds back into energy use, because these are deeply intertwined. And so we're working at it's a trend in research in this field. We're working at an intersection or a nexus of food, energy, and water. And so that's the direction that I'm going to take this. I've worked very closely with Dr. David Heineman at MSU, our chair of our department and the lead of our lab, as well as Sherry Martin. She's another full-time researcher in their lab. And then I've listed 4 graduate students, Quirkus Hamlin, Jake Roush, Bailey Hanna, and actually a postdoc with us, Tian Fang. Those 4 have done a lot of the work that goes into this. As those of you who are familiar with academic research know, the graduate students do the real heavy lifting. And listed there at the bottom are 4 of the major funding agencies that have provided funds to do this research, or the numerous different projects related to it. But also, as Rick mentioned, GLRI and funding through the EPA has been critical, so I certainly should list EPA on this list as well. I'm going to show you some data and maps, and then a little bit of insight in each of those. And I just wanted to provide some background. This is going to be really hard to see in the back. But this is a map. Every year, the USDA, the Department of Ag, does a phenomenal job of providing us with an amazing view of the United States. And that's a view, every 100 feet, we know, quote unquote, what crop was planted. And this is a phenomenal data set that's been available for the last probably decade or so, a little bit less in certain places, that lets us get a view in space and in time of what the landscape really looks like when it comes to agriculture. And statistics can tell us this, but pictures just convey it so much more viscerally. And if you can focus down here, you see most of the agriculture is in the lower part of the basin, especially Michigan, southern Michigan, northern Ohio, but there's some patches of agriculture in New York and Wisconsin as well. And then, of course, it's scattered in many other less intensive forms throughout the basin. And key crops include things like corn, soy, that's no surprise to anyone. Alfalfa and hay are a major crop, especially in less intensively agricultural areas. Dry beans and sugar beets are important crops in the thumb area of Michigan. And then wheat also is an important cover crop, but also can be a primary crop in certain areas. So this is what the agricultural landscape looks like. And of course, this is not to neglect the many important, economically important, but smaller area crops like grapes and various orchard fruits and things like that are key to Michigan and the Great Lakes prosperity. But I'm going to step out and look a little more broadly, because I'm going to be talking about irrigation as one major aspect of how agriculture impacts us. And this might challenge a conception that you have about Michigan as a place that has enough water that we needn't irrigate. And this can be in many cases true. However, there's a lot of conditions where that isn't the case, be it just simply the economic risk of not getting rain at the right time, or contractual requirements for certain specialty crops, or other needs like preventing frost in orchard fruit. So this is a map created from remote sensing, so satellite imagery, of the United States in 2012, showing where the irrigation is. And of course, if you look at this map and you see the intense blue, areas that are nearly 100% irrigated, you wouldn't focus on Michigan. But I do want to just draw your attention to the concentration of irrigation in southwest Michigan, and also a couple of other places in the Great Lakes states, not necessarily in the basin themselves, and that these areas of irrigation are something that are worth focusing on because they have a major impact on water resources in those areas. These irrigation sources are entirely groundwater driven for the most part. There are a few smaller operations that do pump directly from streams, but most of the irrigation in these regions are groundwater driven. And that's part of the reason that I'm going to be focusing on groundwater, is sitting at that nexus of food, energy, and water. So some data. I pulled this data from The USGS, every 5 years, they conduct a survey and an estimate of water use in many, many sectors, including groundwater. So including irrigation. So these data are total irrigation water use in the state every 5 years. And I've grouped them into northern states and southern states just because otherwise there's too many dots and too many lines on a plot. And I just wanted to show you that over the last 40 years, that there has been a substantial increase in irrigated water use. And that is continuing. That hasn't plateaued. There was a big sort of news headline a couple years ago when the latest report was released, the 2010 report, that said that irrigation water use had hit its maximum and had gone down. But that's not true in the humid East and the humid Midwest. Here, we're actually experiencing economic and climate and management forces from an agricultural standpoint that are leading to increased irrigation water use in every state within the Great Lakes. So one of the things that we're doing in our research lab is we're asking the question, well, we've got these fantastic views of what agriculture looks like in terms of what crops are grown, but where are they irrigating? So what we're doing is we're trying to use the same sorts of satellite platforms, the images that are captured on a weekly or biweekly basis, to actually image for us and classify those images where we have irrigation in space and in time to create a sequence of annual maps. We've done this pretty successfully and released a couple of recent efforts in areas like Kansas. But you'll notice that in Kansas, there's a really large contrast between the irrigated circles, the center pivot irrigation circles, and the non-irrigated surrounding areas. So pretty easy to train an algorithm, machine learning algorithm, to find those areas. Much more challenging in Michigan. This is a view of an just as intensively irrigated portion just to the south and west of Centerville, Michigan. And you can see that there is a lot less contrast there between the wet areas near streams or simply open fields that got enough rain that year. So we're working on solving this, taking the methods that we've developed and applying them, but also, because it's research, encountering a lot of challenges. And this is the work of our postdoc, Tianfang Zhu. So this is one of our active areas of research, and we're achieving success, and we're not quite all the way there. But what we hope to get a better idea of is to go along with that single dot for Michigan, how much irrigation is there in space and in time. Another big effort has been to quantify that same sort of view that we see for crops, but do it for nutrients, agricultural nutrients, plant nutrients, nitrogen and phosphorus. How much has been applied? And in this sense, we've focused on just one sort of slice in time. We've chosen to focus on 2010 because it's an intense sort of effort. And what we've done is we've focused on 7 different distinct sources of nutrients: atmospheric deposition, septic systems, urban fertilizers like lawn fertilizers, point sources, which I'm not showing on this map, agricultural manure, nitrogen fixation by certain crops like soybeans and other legume crops, and also hay and grasses, and then, of course, agricultural chemical fertilizers. And trying to describe each one of those sources at every 30-meter pixel is an enormous challenge, and one that we've been working on for quite some time. But recently, we've completed this set of maps, and we're working on publishing it later this summer, or submitting it for publication. But it gives us views like this. In some ways, not a surprise, but in those detail, give us the ability to help and start managing these nutrients more effectively. These are what are applied to the landscape, and you see there are some intense hotspot areas. The Thumb area of Michigan, in the St. Joe River Basin, the Maumee River Basin, which is a huge contributor to the problems that we're seeing in the western Lake Erie Basin. Also areas of large manure sources of pea being around Green Bay, and also in western upstate New York. So if we take these maps and then we say, okay, well, let's look at them by lake. Let's kind of characterize the differences within each lake in terms of their nutrient source breakdown. I apologize for the somewhat haphazard color scheme, but in purple, pink, or red here, we have the agricultural sources. And you see that for nitrogen, they provide something like 70 to 80% of the nutrient sources for each lake, which is a bit of no surprise, but it does show that the Great Lakes Basin is not some monolithic entity to be managed. There are unique combinations of sources and therefore solutions, policy-wise, within each basin, and that's certainly the approach taken by the Office of Great Lakes and other people that implement lake-wide area management plans. And so those sources vary by if they're nitrogen or phosphorus, and there's certainly a lot more data in there to be broken down. Another thing, focusing on groundwater. So the reason I'm taking a groundwater perspective is that Michigan and much of the Great Lakes Basin is very permeable. Its soils are very permeable, meaning we don't get a lot of direct runoff. There are direct runoff of water to streams. There are areas where that's not true. The Saginaw lowlands area, the lower western Lake Erie Basin, in those lake plain areas can see a lot of runoff directly to the river. But mostly, the avenue for nutrients to travel from the field or other non-point sources to the stream is through the groundwater system. And so we're taking a look at something called groundwater sheds, which is the surface watershed concept applied to groundwater, and seeing that there are some pretty substantial differences when you say, well, I'm going to look at a particular section of a stream and say, what is the groundwater shed for this, and let me compare it to the surface watershed. This map takes the so-called Huck 12 set of watersheds, which is a standardized product from the USGS, and compares in areas that are dark green are where their surface watershed and the groundwater shed are shared. In light green is where they're different, meaning there are substantial areas within Michigan where if you want to manage water quality in that stream, you need to understand not just your surface watershed, but also your groundwater shed, this new focus on groundwater. And just to give you a particular example, up here, this is in this box, is where the Jordan River watershed is. And if you're familiar with the Jordan River watershed, it's a gem of lower Michigan. It's a wild and scenic river. It was designated that in the late 1960s. It's a fantastic place to fish. It's a beautiful recreational destination and something which we absolutely would like to preserve. The Jordan River is in a really cool setting from a hydrologic standpoint because its surface watershed is much smaller than its groundwater shed. It gets a ton of extra water, and this provides a stable flow of water in the stream year-round, which makes it a fantastic salmon and brook trout spawning habitat, as well as a fantastic recreational destination. It's really fairly unique in the entire country. The area has seen a lot of growth, in particular in this area. I'm zooming in now to this area. It's seen a lot of growth in irrigated potato farming. And I'm not meaning to point the finger at anyone. It's a vital part of the local economy up in the Mansalona region. But that expansion of irrigation, here we see pre-1993 in red, post-1993 in yellow. This area has transformed itself into a large irrigated region, where if we zoom in on our non-point source map of nitrogen, we see there's a real hot spot of nitrogen. And when we did sampling around the state a few years ago, back in 2010, we saw the Jordan River stand out as a place that, despite its largely wild and unmanaged land use, it had a nitrogen problem. People blamed the fishery that sits there. And as part of the GLRI, the fish hatchery in the Jordan River got funding to build a better on-site wastewater treatment plant. But the problem isn't fixed. And the reason is because of that groundwater shed and the management that needs to occur outside of the surface watershed. Groundwater can also bring along legacy. This is the Huron River watershed down to our southeast. And in the Huron River watershed, this is a map of modeled groundwater travel time. So we can't measure this directly, not like this. But what it shows in those hot colors are places where it takes as many as several centuries for groundwater to travel from the point where it enters the water table to the point where it discharges into a stream, wetland, or lake. So obviously, if it takes that long to travel, the surface was different back then. So if we want to understand how land cover and land use impact our water resources, we need to look back in time to what the landscape looked like when that water was initially recharged into the aquifer. So we've taken this perspective of the groundwater travel time-based land use legacy to understand, in this case, if we look at all these areas in magenta are areas where the land cover was different when that water was recharged than it is today. So we really need to take this sort of long view in both space and time to understand how our water supplies are being affected. And I do want to mention briefly the perspective of climate change. And the angle I would like to take on this is, regardless of how you perceive this issue, and it's certainly something which in my field of ag and water, there's a wide range of views. There is one set of facts, and that's when you look backward, you see that there is a major difference in terms of what farmers were doing in 1970 and what they're doing today, or excuse me, late 1970s. This is a plot, I'll explain just a little bit, where I've pulled for the first week in May for my northern state group and the last week in April for my southern state group, what percentage of each state's corn crop has actually been planted. So again, the USDA takes fabulous statistics. They're really second to none. They provide this information every year, and what we see is in those states, in every state except for Ohio, there's a significant increasing trend in the proportion of the crop that has been planted by that time. So in other words, farmers are planting earlier and earlier, essentially a week earlier than they did 35 years ago. Okay, so regardless of what you think about potential future climate change or climate change in the past, it is happening, and the people who have to adapt to it first are farmers. And so communicating complex messages about water resources, climate change, and how we might adapt and form a resilient future really have to take into account those perspectives. And that's something that we've actually worked pretty closely with the Sea Grant and others in doing. So just to leave you with a couple of last words here, these have some policy implications for the Great Lakes. And that agriculture is the dominant source of nutrients, and it's a rapidly growing consumer of water resources. That groundwater is the primary means of nutrient movement across most of the basin, and it's really slow to respond to surface change. So it's not the same as surface water, and we need to understand that in our management. Now is the time to take this into account, to get ahead of the trends that we see already, to take action so that by the time the surface effects are felt through the groundwater system, we can actually see positive change in our water resources. And finally, that this is a real science-driven effort to bring knowledge from these fields directly into policy and regulation. And Michigan has taken great steps in this regard with the water assessment tool, and that's certainly something we'd like to see more flexibility with in terms of both policy as well as a regulatory perspective on integrating the latest research, the latest really well-vetted research into management and policy making. And I'll leave you with that there are many, many groups who are taking a proactive approach to doing management, if not at the state level or at the federal level. Of course, there is a lot going on. There's a ton going on locally as well. And the site that I had up there, the Tipping Point Planner, is a site that was developed by the Illinois-Indiana Sea Grant in collaboration with Purdue. And then the science from it came from Purdue, Michigan State, U of M, University of Minnesota, a couple universities in Ontario. And we've brought that together to offer local planning groups a better tool to manage their watershed planning, things like 319 plans and so forth. So those are the remarks I wanted to leave you with today. Thank you.